All right, everybody. In today's teaching session, we are going to switch gears just a bit here and look at SQL instead of Python. Okay, most of my videos are based on Python. I did one pertaining to SQL a little while ago. I think that one was pretty successful. I think it turned out quite well. So I just wanted to show you how to get a free copy of SQL Server Express. As long as you have a PC, you can get this for free. This is the URL. I'll share this URL with everybody here, and I'll share the Jupyter notebook. I actually did create a notebook. Just I like working in this kind of environment. It's pretty neat. It's pretty tight, pretty crisp, I think. It's a good way to present data, even though we're not even running any code. Right? This is all SQL code. You can't even run it in a Jupyter notebook. But I mean, you can inside of a string. Let me take that back. You can run this inside of a string and then query a database and then push it into a data frame, of course. But we're not running it in the we're not running SQL in the notebook itself. Okay, so I just want to share this with you and this link over here. Okay, that's where we can get the free version of SQL Server. Let's switch over to SQL Server right now. Okay, so I picked about, I think this is 15 different queries. How many we got here? 15, 14. 15, yep. Okay, so we have 15 queries I think are very interesting, very useful. You'll see this a lot on interview questions, but it's very practical too. You'll see that people using this in the SQL world all the time, right? So that's why I put these 50 together. I think it's pretty common and extremely useful in all kinds of environments, right? Certainly the business world, finance. I don't care if you work for the government or education or nonprofit or anything. SQL is so ubiquitous. You really see it everywhere out there, right? So I think it is good to know this stuff. So there's a little terminology. Let's get this out of the way. DDL is data definition language. These are commands like create, alter, drop. If you're going to drop a table, create a table, create it. You can make alterations to the table, to the primary, whatever you want. So DDL is the data definition language. DML is data manipulation language. These are commands like insert, update, and delete. So you'll see this used quite a bit. The DDL is not quite as frequently used, I would say, because once a table is created, pretty much done unless you drop it and recreate it. I think you'll see DML used more often. And of course, the DQL, the dQuery language, is by far the most common. And these are things like select, from, where, things like this, right? So that's the terminology. So we can go ahead and run this. We can select this one-liner right here, hit F5 to run it. Okay, and it goes pretty fast. So we just dropped the table. So that is the DDL. You can see the DDL right here. We dropped the table, and also DDL. We're going to create a table. Okay, just to clean up the environment. Now, if the table is already created and you try to run this, I hit F5 to run it. You get error, right, because it's already in the database. But if you drop it and then recreate it, everything works fine. Okay, so that's exactly what I expect. So the DML is the data manipulation language. Let's go ahead and insert some records into this table. The table is named employees. Right now, if I refresh this over here, go to here, refresh, go to my tables and look at employees. It's going to be empty, right? Because I haven't done anything to it. Select top 1000. Okay. Nice. Okay, so it's empty, right? There's no records there. So let's go here and select F5. I'm sorry, select the text to the 5 runs, and we get this message down here. Rows were affected, and if we go ahead and refresh that, F5 to refresh it, there's the data, right? So everything's working just like we would expect. Okay, and there's another way to do the same thing. Select all from employees. Now here's the first question. Let's say this is what are we trying to do here? We're going to find employees who are in the same department and look for salary differences greater than a specific amount. Okay, so that's what this query is doing. And this is very relevant, right? We're looking at the employees that have salary greater than 5,000, and we're going to look at employees across different departments. Okay, so this is actually called a self-join. You're joining the query to itself. So you have this E2 is an alias and E1 is an alias. Okay, we're joining on this line right here. Here's the join. Well, the join, and we'd have to join on something. We're joining on department ID, so it ties this query to itself, right? So we're querying one single table let's run it, select F5 to run. And there we have it. So we have a where clause, right, where salary from employee 1 is greater than employee 1 minus employee 2 is greater than 5,000, right? Okay, so that is the join on that department ID. And normally you will join on IDs or some type of unique identifier, some type of record that can identify these people rather than joining on things like a name or a date. You could do that, but that's pretty rare to actually do that. Normally you're going to join on some type of ID, right? So that's fine. And the query, essentially, in my notes here, I have the query only compares employees within the same department, okay? And we're not going across departments, okay? So that is pretty useful. Here's another example, a correlated subquery, and this can be used to filter out rows based on aggregations as they're calculated per row, okay? So this can be useful to find employees whose salary is above the average salary of their department. So why would you need to know this, right? Why would you have to know the average and who's greater? Well, who's getting paid more, right? Across the average of the whole department or the whole team or whatever the breakdown is here. So again, you'll see the E1 and E2, so employee 1, employee 2. Okay, we're taking the average salary, and here's the where clause, right? Where employee 1 salary is greater than this average over here, okay? So if I select that and run in between, it's not going to work, right? Because it's a correlated subquery. So the inner part of the query has to be shaped for the outer part of the query to work. Okay, this is a subquery. If it's not able to calculate, the whole query would have to be run like this, F5 to run it. We can see the salary, the department ID for the person, and then the average salary. And these are all look correct, right? So that is greater than that. That is greater than that. That is greater than that. And that is greater than that, right? So this is working. And with the correlated subquery, it's all or nothing. You can't just run the subquery. And sometimes when you have a non-correlated subquery, you can run the subquery. But when they're correlated, they cannot run separate, right? Because they're bound together. That's why they're considered correlated. So again, we're joining on the department ID. So E1 is employee 1, E2 is employee 2. So we're joining the table to itself and using a correlated subquery to get those averages and people's actual salaries. Okay, so good stuff, that's working. So non-correlated subquery. So this is what I was just talking about, right? So if we want to look at non-correlated subqueries, this should be perfectly fine, right? This is a subquery here, and we get a result of 64461, okay? So in this case, the subquery runs, right, because it's not correlated to the other query. But when you combine them together, it does something pretty interesting. It'll help you filter out employees whose salaries are above the average salary for the whole company. So now we're not looking just by department. We're looking for the department, the entire company right here. And we have the salary and then the average salary. These happen to be the same here. Okay, but salary has to be higher than the average, right? So that's what we're looking at here as average salary, average for employees, average and average, right? So this should work too, right? If we pick this part and hit F5, come employees is invalid. Oh yeah, we need the aggregation because we're doing we're doing this right here. So that will not work by itself. We'd have to have a group by name and salary because we're aggregating this. Anything that is not being aggregated has to be grouped by, right? So we have to group by this over here. Group. Okay, and then F5. Group by name, salary. Oh, we forgot the comma there, okay. Okay, then we have the salary and the average, but that's getting going down the rabbit hole there. So really, you can run these queries separate, but you have to handle them a little bit different, right? And that's not even the objective anyway. We want to find the average salary per employee and then compare that, I'm sorry, the salary per employee, and then compare that to the average for the whole company, right? So that's pretty useful. So here's an example of a hierarchical query. So these are helpful when you're working with hierarchical data. Wait, create table organization. There's already an object named. Okay, so I must have done this earlier today. Drop table. Drop. Okay, that's like the example we saw at the beginning, right? So if the object exists, you can't create it, right? Because it's already in there. So that's fine. So we create the object, and we are going to use our DML to insert data into the newly created object. Okay, 14 rows affected. And then if we go look for this into organization, let me just refresh this. You have to refresh it or the object doesn't show up, right? So once we go down here to organization, just want to get a quick look at this right here. Okay, nice. And there's the data. So this is the boss, the big boss right here, because there's no manager ID. So that would be the CEO or the highest ranking employee in this table, right? So I don't need that. I can close that. And that was from before. Yeah, that was from earlier. Okay, we don't need that right now. So we inserted the data using DML, and now we can start to run our hierarchical query. And this is going to basically start with the comp manager and run this over and over, okay, until we pick up all the records right here. So we have the object named hierarchy, selecting all from hierarchy, okay, and this all has to run at the same time too. If you try to run this, it doesn't exist, right? So that could throw an error. If you try to run this, it's not going to work, right? So you have to select everything. It all works together. It's all bound together. So we run this, and we get our results, and then the level that this person works at too. So these two people are at the same level. These number 2s are at the next higher level. 3s are actually at the 3, and this 4 is at the 4, right? So that's fine. And these are useful for any kind of recursion, anything that has to be done over and over, and you'll know how many times that you have to do it, right? Until you pick up all the records. It's going to keep working, running over and over and over until it retrieves every record in that table, and then it spits out the results to you. That's what we got here. So this is interesting because we create the object on the fly. It only exists in the memory, right? If you look over here in this view, you won't see any kind of hierarchy, table named hierarchy, because it doesn't exist. It only exists when you run it, when you select the code and hit F5, you get the results, right? But it doesn't really exist in a permanent state, right? It's just a temporary table. So we're joining hierarchy. H would be the alias on e.manager ID equals h.manager ID. So this is, I guess E would be the employee, and the H would represent the hierarchy of the employee's ID, right? So that's pretty cool. That's pretty useful too. Okay, number 5, using Windows functions. This is extremely useful. I do this all the time for any kind of running sum, ranking, dense ranking, creating row numbers, whatever you want. Windows functions come in very useful for all kinds of things, right? So if we look here, we're going back to that employees table that we were looking at before. We're ranking the employees, okay, over the partition by department ID and order by descending. So you always need an order by, so it has to know which order. Is this going to be ascending or descending? And you have to partition by something. In this particular case, it's by department ID, and you can see the rank is listed under the department ID, right? I'm sorry, the department ID determines the rank. So here's department ID 111, and here's the rank based on salary 123. Okay, so here's department 2. We have 3 records for 2, and here's rank 123. Right, here's the highest, second highest, and then third highest, and here's department 4. So we have highest, second highest, and then third highest. Right, there's the ranking. So the Windows functions are very useful for any kind of rank, row number, dense rank, running sum, and so on and so forth, right? So very useful. And again, you have to use the partition by. In this case, we pick department, and the ranking is done over the salary, right? So rank over, hopefully that makes sense. What are we going over? This partition right here You can kind of think of a partition by similar to a group by, but group by will condense everything into one row when it does the grouping. The partition ID leaves everything in the original state, right? So all the records are still visible. Nothing is being compressed out, okay? So hopefully that makes sense. Okay, this is pretty useful too. This comes up a lot actually. So exists and not exists. Exists can be useful for testing if any rows are related to rows in another table. Okay, so you see this a lot in the real world. Create table students. I think I already have my students. Let me just drop it and then recreate it. So I'm going to error ERP students because I have the DDL, so I might as well just drop it and recreate it. Kind of a moot point. Doesn't really matter. Create courses table, and I think I already have the courses. I'll just do the same thing. Courses. Whoops. Okay, and now do the DML to do the insert, and then the DQL. Okay, so 3 rows and 4 rows, perfect, just what we're looking for. Now here's the DQL. So with the exists, we're using this in the where clause, okay, and we're looking for basically which records right here, or which courses. What was it doing? So it's looking for the student.course ID matches the course.course ID. Okay, so we have course ID 1, 2, 3 over here, and then student ID 1, 2, 3 over here. So we're matching on the IDs, right? That's a typical way to do that. And we hit this, and we can see these courses exist, right? Math, physics, and chemistry, and they all exist because we have the 1, 2, 3, 0. Okay, so the not exist would do the opposite. The exist is similar to an in clause too. There's also an in and not in. I think with the in clause, it handles null slightly differently. So in some cases, the exists or the in is going to produce exactly the same results, and the not exist and not in will produce the same results. But I think it could actually be different. I'd have to Google it now. I forgot. I think somehow it handles nulls a little bit different, right? So if your data has no nulls, the result will be the same. If there's nulls in there, you have to figure out what is going to be better for your specific use case, right? Yeah, and just like it sounds, it's used to check for the existence of related rows in another table, right? Okay, so returns all the same output as above. So if I did this, there's another way to do exactly the same thing. In the SQL world, usually there's at least 2, 3, 4, sometimes 5, or even maybe 6, even more ways to do exactly the same thing. Because SQL is a pretty rich language, it's pretty evolved. It's been around for, I think by now, I think 30 years. Google that one too. It's been around for quite a while, so it's a pretty mature language, and you can really do a lot with it, right? You have to figure out what you want to do, and then set it up and then run it, right? But it's interesting though that these two queries will have the same output, right? Okay, so moving on. Aggregations with having. Okay, so this again, it's very practical. Use these things all the time. You select average from group by. Okay, anything that is not being aggregated. In this case, it's employees. You have to group by the department ID. Right? If it's being aggregated, then you'll see some kind of sum, count, average, whatever type of math you're doing there. That is going to be rolled up by group ID or group by, right? And that is the item that we're grouping by. And we're basically using this having clause as a filter, okay? So the difference between where and having, the where comes before the group by and having comes after the group by, okay? So having filters after group by is usually preferred. It's typically used to filter aggregated data, and having enables more complex conditions than just what you can get with a regular where clause, right? So having is very useful to have in your toolbox. Okay, useful to have, right? I guess I think that makes sense. So, so here's how we would do it with the where clause, and we would get the same results. Okay, so if I run these two together, okay, same exact outcome, right? The only difference is or is it here? I think this one is just a little bit harder to follow, actually. I think this setup is just a little bit more complicated because here you have a subquery from employees as department average. See, so if I run that, this subquery will run because it's not correlated to the other query. But overall, I think this is just a more complex beast to set up and to maintain. And this is actually pretty simple. Some of these queries get very, very complicated. So the easier you can write the code and the simpler you can make it, the simpler your life is going to be, right? If you set up this query and then run it, everything looks fine, you go away, and then 6 months later you have to make some changes to it. Are you really going to remember all the details of what you were doing at that point in time 6 months earlier? Or you can remember why you created the query. I mean, again, this is pretty simple. It's pretty straightforward stuff, but some of these get very complicated, right? So you want to make your life as easy as possible, make your SQL as easy as possible to read. And by the way, use notes too. If you have two dashes right here, this is considered a comment, right? The line is commented out. So notes are very useful. When you put your code away and then go back there 6 months later, you can remember what you're doing. And even the more important question to ask is why you're doing it. That's probably the number one question. Why were you doing this query? What's the point of the query? What's the purpose, right? If you have some notes or some comments in there, it's a lot easier to remember this stuff. Okay. So moving on, union for combining results. This is great if you're stacking data, one thing on top of another or one thing underneath another. Okay, we have our DDL, here's our DML, data manipulation language, run it, rows affected, and then let's run this from employees. Okay, I'm gonna run these separate and then together. So here's on employees, we have 13. Okay, I saw a little 13 down here in the bottom right, that's why I knew that. And from employees, former employees, we have 7. Okay, so 7 and what was that? 14, 13, right? So 20 total, but really have 7. I think this is going to get us the duplicates. Okay, union all will show us the duplicates. Now we're back to 20 rows. But if you just use union, the duplicates are filtered out, inherently filtered out. Okay, so now we have 17. So that's something to be aware. And you can see how the data is stacked one underneath the other, right? When you union it together, the column names just have to match up. That's the only thing you have to be careful of, and make sure that the when you're putting this stuff together, make sure that you're lining columns the right way. Here we only have one column, so it's very, very simple. It's very straightforward. But if you get into larger unions where you have dozens and dozens of rows that you are unioning together, you just have to make sure that everything is lining up correctly. Okay. Case statement. So case is very useful when you are trying to classify something into different buckets or get something into different bins. Right? If I hit F5, we can say these salaries are medium, high, medium, and low based on this logic right here. Right. So here's the case. One salary less than 50K, that's low. One salary between 50 and 70, that's medium. Otherwise, it's high. So pretty simple, pretty straightforward, very useful. Okay. So cross join for combinations. Now, the cross join can be used to create combinations of 2 or more data sets. Usually, you would see this in some type of recommendation system, perhaps. Okay, it generates all the combinations of departments, employees, names, and there's uses for this. This isn't as common as some of the other queries that we saw. But if you need different combinations of something, then the cross join is your go-to, right? That's going to do it for you. So here's an example: sales, and then name. So here's all the sales people in the sales department. But it doesn't mean that these people work in the sales department. You see that? So let's look at the first one: sales John Doe. Okay, and then engineering John Doe, and then marketing John Doe. Okay, human resources John Doe, finance John Doe. So basically, it's creating a combination of everything. So again, this could be very useful in some scenarios, but it's not quite as common as some of the other queries that we saw before, right? And this is actually pretty interesting too. There's actually no join here. See here, we're using a cross join. If you just select all from employees and departments, there's actually no join syntax right there. So again, you'll get your combinations: John Doe, sales, All right, we just saw that John Doe engineering, John Doe marketing. So it's getting all the combinations, but you actually don't have a join down here. So you have no join. Because you're just taking all the combinations of everything, not joining anything together. Okay, so moving on, intersect returns all the rows that are common in both data sets. Okay, if you think about it, anything that intersects both data sets, we saw those duplicated names before. All right, so these names, this is a great way to check for duplicates or just items that are similar in different tables, right? The intersect is going to do that for you. And this is kind of the opposite, except is showing you anything rows from the first query that don't show up in the second query, right? So if you take former employees and put that over there, you take employees and put that down there. So we'll get a smaller list, I believe. I haven't looked at this yet. Yeah, a smaller list, that's what I thought. Okay, so there's just fewer people in this former employees table, and there's more in this table. And you just look for whatever is in the, oops, not exactly what I want to do. Let me fix that. You look for anything that's in the first query that doesn't appear in the second, right? So that is pretty useful too. Okay, and then for finding duplicates, there's one way. There's a few different ways to do this. Like this, it's pretty straightforward. So this guy shows up, this name shows up twice from the employees table. Okay, so we're counting all, we're getting the name and then the count as names where the count is greater than 1. If I do greater than equal to 1, then we'll see all the names, right? So there's all the names. And this guy was duplicated, but we really want greater than 1, right? So any kind of duplicates are easy to detect. You're counting like that, okay? So running some, we saw the partition by again, partition by department ID, just like before, order by salary and ascending order. I believe the first time we used this, it was descending order. Okay, it can be whatever you want. And then you can see the running sum by department ID. So here's 5,500. And then you add 60,000 and then 7,500. So you can see how the sum is running up by department ID. Here we have 58K, 67, 73. So 58 plus 67 is 125, plus 73 is 190. And that is department number 2. And I think we figured this out. 5,200, 110, 196, and 291 is summing up these. Okay, so again, pretty useful. And we are at 15. This is nice. We kind of went through this pretty quick. Drop table just to be consistent with the others. I'll drop that, rebuild it. So there's my DDL. Okay, you're gone. Now you're back. I'm going to insert the data using DML. Okay, 10 rows. And if we take a quick look at it, what's this thing look like? Okay, so we have John Doe, James Smith, department ID, day of the week, and attendance status. Okay, so now let me take a max case. When day of week is Monday, we're doing a max query in this case. Okay, so basically taking and pivoting the data in a different way. So this is useful for showcasing data if you just want to flip it, if you want to pivot it, if you want to display it differently. I wouldn't say you should store the data in the database, but it's pretty cool how you can do these pivots. And I think I have a pivot right below, right? So this is sort of like a artificial pivot. We're forcing the max case to take the data from what we saw before and flip it. So this is called long format. This is called wide format. You pivot it or pivoted, wide or pivot, again, long or unpivoted. We can see the same thing with this. I haven't looked at this code lately. I think this does exactly the same thing. Yep. So there's 2 different ways to pivot. You have all the select items over here. Here's the table name. Maximum attendance status for day of week in Monday, Tuesday, Wednesday, Thursday, Friday. So you're actually running a small loop here, and you're calling this object of pivot as PVT, and this is the magic that's doing the work for you, right? So pretty cool. So pivot with case or using the pivot clause, you can achieve the same functionality. Like if the code, I would say personally, if the code was a little bit smaller, this might be doable if you had a huge table or you had many items like this over here, Monday, Tuesday, Wednesday, Thursday, Friday. It's only 5, so that's not bad. I think this is a little cleaner, easier to set up and easier to maintain, but could be just a personal preference. Maybe the max in case when is a better option for you. You really have to understand what you're trying to achieve and then try to execute it smoothly and as effortlessly as possible, right? You want your code to be clean, crisp, clear, readable, have notes in here, right? Whenever possible. More notes is better than less notes. And that's it. But try to keep these things as simple and straightforward, as streamlined as possible, because they probably will grow more complex over time. And if you have just really hard to read code, it's going to become a nightmare. I've seen this happen many times. It's going to become nightmarish over a long period of time. And it's going to make your life just quite miserable. So don't go down that path, please. Keep these things as simple as possible, but they have to work too, right? So you have 15 good ideas here. I threw this together, I think like last weekend. I finally had time to record the video. So that's pretty much it. There's more to SQL than just this, but I think these are some of the more common techniques. I've been in the finance space for close to 20 years now, and I've seen these types of things show up over and over and over. There's a few other things you can do with SQL. There's quite a few things you can do, actually, but these are probably by far some common things that you'll encounter in your career. So that's pretty much it. Hopefully that was useful. Hopefully you learned a couple new things today. I learned a couple new things. I was putting them together. Okay, that's it. Thanks so much for your time today, guys, and enjoy the rest of your day.